Number one, if it's an improper rational function, meaning the degree in the numerator is greater than or equal to the degree in the denominator, then before we start trying to find the antiderivative, we do polynomial long division to it. If we come across a proper rational function, or even in some cases where our long division gives us a remainder divided by denominator that is a proper rational function, there are cases where we can't yet take the antiderivative unless we do partial fraction decomposition next. And so the idea is long division first, if you can do it, and then partial fractions next, if you can do that. And then once we're done doing long division and partial fractions, we're going to end up with one of these four cases. Maybe I have a term with a constant in the numerator and a linear factor in the denominator, like this. Well, then the antiderivative is just going to be the natural log. Okay? In the second case, I've done long division, I've done partial fraction decomposition. Maybe I end up with a term that has a constant numerator and a repeated linear factor in the denominator that has multiplicity 2 or 3 or 4 or whatever. And in that case, I can just use the antiderivative power rule, where the power rule would say, make that -5 divided by x minus 3. In the third case, maybe I've got a term that has an x in the numerator and an irreducible quadratic in the denominator, like when you're doing partial fraction decomposition, and maybe you end up with a quadratic factor that looks like this, and we don't really want to factor that because then I get imaginary numbers. If that happens, and maybe I have, like I said, something in the numerator with an x, this can be found using a u substitution where I set u equal to x squared. You're close. Yeah, just set it equal to x squared plus 1, that whole quadratic factor. Then the du is the same thing as 2x dx. So when I see 2x dx, I can replace it with the du, and I get 1 over u, and I can take the natural log of u and then plug in the u and everything, and it works. The last case is what happens if I have a constant in the numerator and an irreducible quadratic in the denominator. Well, this would be a case when I have to use trig sub, which is the strategies we talked about on Friday, where you see a pattern like a variable squared plus a constant squared, and you write down something like u equals a tangent theta, secant theta, sine theta, and you draw a triangle and you label it and blah, blah, blah. That would be a case for trig substitution like we did last time. And that's it. That covers like all of your bases for looking at real valued rational functions in the integrand. So like I said, nothing new, right? We've already done long division in this class. We've already done partial fraction decomposition in this class. We've already done u substitution. We've already done trig substitution. This is just a matter of putting it all together, where anything can happen. And if you know those strategies, you can do any rational function. Like this one. If I were taking the antiderivative of 1 divided by x squared minus 5x plus 6, I'm first going to do decomposition. And decomposition would look like saying this integrand is the same thing as 1 divided by something times something. How do I factor that? Yeah, x minus 3 times x minus 2. And so this, after decomposition, is going to be equal to a divided by x minus 2 plus b divided by x minus 3. Or in other words, 1 is equal to a times x minus 3 plus b times x minus 2. And then we like to use that Heaviside method where we say if x is equal to 3, then b is equal to 1. And if x is equal to 2, then a is equal to what? -1. So to remind you, we choose convenient values of x that are the roots of the factors because those will zero out one of the constants we're looking for, and that makes it easier to solve for the other one. And if that's true for one value of x, it has to be true for all the values of x, right? This equation, what I wrote down, is supposed to be true for every real number value of x. So if I just choose any real number value of x, I should be able to solve for the constants. And so this integrand is now the same thing as writing the antiderivative of -1 over x minus 1 plus 1 over x minus 3. I think I misspoke. -1 over x minus 2 plus 1 over x minus 3. And then this makes it really easy to find the antiderivative. This is just negative natural log of absolute value x minus 2. Sorry, it's supposed to be an absolute value. And natural log of absolute value x minus 3 plus c. Not bad, right? Okay. Do some more interesting examples. Find the antiderivative, and this time I've got a cubic polynomial in the numerator and a quartic polynomial in the denominator. This time we're going to find the antiderivative. Again, since this is proper, right, 3 is less than 4, this is a proper rational function. I don't need to do long division to it. Instead, let's do the partial fraction decomposition. And how does this denominator factor? Yeah, x squared plus 9 times x squared plus 9. That works. So that's a repeated, irreducible quadratic factor. And hopefully you remember how to do this. With quadratic factors, we have to put ax plus b, a linear form, in the numerator. And for repeated factors like this, we've got to continue to list them until we reach the power that we see. So in this case, I need I need it to look like this after decomposition, where we're trying to solve for constants a, b, c, and d. So then we write 5x cubed plus 45x plus 3 is equal to ax plus b times x squared plus 9 plus cx plus d. And we want to break this up into the powers of x, right? Like we'll write one equation that represents just making the left side 5x cubed equal to the right side. And what's the only term that contains x cubed on the right side of this equation? Ax cubed. And then on the left side, I've got 0x squared. On the right side, what's the only way I can get an x squared? Bx squared. On the left side, we have 45x. And on the right side, I can get x from 9ax and what else? Cx. And then the last thing is the constant term. So I set 3 equal to the constant term on the right side, which is what? There we go. So solving this system is not terribly hard. First of all, b is equal to 0 from here, from that second equation. So that doesn't matter. What is a equal to? 5. So when it says 9 times ax, that's 9 times 5 times x, which is 45x. So what does that make c equal to? 0. And then d is 3. All right, so I can now write my rational function in decomposed form by writing 5x divided by x squared plus 9 plus 3 over x squared plus 9 squared. And this is the rational function I'm trying to take an antiderivative of. So now imagine we're trying to take an antiderivative of this with respect to x. And it's going to make more sense to treat these separately, right? There's going to be a different strategy used for the left term and the right term. And so with that antiderivative additivity, we just break it up into two separate little antiderivatives. And to solve the left one, I'm going to use the color blue. And for this blue one, what is the strategy I'm going to use? I solved the blue one.
Trig substitution?
I actually don't need to use a trig substitution. I could, and trig substitution would work, but it's not the easiest thing to do. Like trig substitution normally takes a lot of time to work through. There's an easier method. I think I could use a u substitution here. And my u substitution would be setting u equal to what? X squared plus 9. And that way, the derivative of u with respect to x would be 2x. And so I can replace x dx with 1/2 du. And I see an x dx in that numerator of this integral. And so we're going to write antiderivative of 5/2 1/u du. What's the antiderivative of 1 divided by u?
Natural log u.
Very good. Natural log of u. And then the u is just x squared plus 9. And so this part is 5/2 natural log of absolute value x squared plus 9 plus c. Okay, now that's 1/2 of it. I also have to do the second antiderivative over here. So I'll switch to orange and solve this other one, which is 3/x squared plus 9 all squared. What's the strategy I should use for this? The orange one. Yeah, this time I have to do trig substitution. So I'm going to write that down again, lower down here, because it was 3 divided by x squared plus 9 squared. Okay. Knowing this is a trig sub, do I write u equals a tangent theta, secant theta, or sine theta? Tangent. Yeah, if I see a variable squared plus a constant squared, that tells me I write u equals a tangent theta. Here, the u part is just x. The a part is 3. Yeah. Because what we see here is like a u squared plus, or sorry, yeah, u squared plus a squared. So we're going to use the substitution x equals 3 tangent theta. And now we draw a triangle. We label this theta. We make this a right angle. And on my triangle, tangent theta is the ratio of the opposite side to the adjacent side. And that has to be x/3. So the opposite side is x, and the adjacent side should be 3. On my right triangle now, what is the length of the hypotenuse?
X squared plus 9. Well, square root of x squared plus 9.
There you go. The Pythagorean theorem says this hypotenuse should be square root of x squared plus 9. So this is the tricky part, is like, I see the x squared plus 9 in my integrand. I see the x squared plus 9 on my triangle. How do I get something like, how do I get this to sort of match up? What kind of trig function looks like my integrand? Well, this is a question you've got to ask yourself on the test. I'm not going to tell you where to look, but if I had adjacent side over hypotenuse, I would have like 3 divided by square root of x squared plus 9. That's kind of close, right? What trig function is adjacent divided by hypotenuse? Cosine. Cosine of theta would be the adjacent side divided by the hypotenuse. But I don't have 3 divided by square root of x squared plus 9. I've got 3 divided by x squared plus 9 squared. And so I should raise both sides of this equation to the 4th power. What's 3 to the 4th power? It's 3 times 27. Yeah, 81. So now we can write this as the antiderivative of cosine to the 4th power theta dx. But I also have this 27, and that means I need to divide by 27, right? Because my integrand is just 3 divided by x squared plus 9 squared, not the times 27 part. Okay. I have a really bad habit of forgetting to do this, so make sure you don't forget to do this. I still need to take care of this dx. And so to take care of this dx, we've got to go back here. Should go back here. And if this is x, then the derivative of x with respect to theta is what? 3 secant squared theta. And so if I want to get rid of this dx, I need to replace the dx with 3 secant squared theta d theta. And now we do that. This 3 from my dx divided by 27 is going to simplify the fraction 3 27ths to 1 over 9. And then I'm going to have cosine to the 4th theta secant squared theta d theta. And how does that simplify?
Is that just simplified to cosine squared of theta d theta?
Great. Very good. Yeah, cosine and secant are reciprocals. So those are going to cancel each other out to just cosine squared theta. And cosine squared, we need to use our power reduction identity, which says cosine squared is the same thing as 1/2 1 plus or minus. You know what I'm talking about? It's plus. 1 plus cosine 2 theta. Yeah, you got to remember those power reduction identities. They look really similar. Cosine squared is 1/2 1 plus cosine 2 theta. Sine squared is 1/2 times 1 minus cosine 2 theta. So in both cases, for cosine squared and sine squared, it gets the cosine 2 theta part, right? It looks exactly the same. The only difference is because it's a cosine, it's positive. If it's a sine, it's negative. The only thing that changes is the plus or minus sign there. Okay, so knowing that trig identity, now we've got 1/9 times 1/2 times 1. The antiderivative of 1 is theta, so we're talking about 1/18 theta, the antiderivative of cosine is sine, right? And in the antiderivative, I'm also going to multiply by an extra half. So that's going to be 1 over 36 sine of 2 theta plus c. Now we're not done, because this is an answer in terms of thetas, but I actually want an answer in terms of x's. So I've got to go back to my triangle over here and figure out what would sine of 2 theta be. Well, this is, again, it's annoying how many trig identities we use in calculus 2, but sine of 2 theta is equal to what? What's the trig identity I'm searching around for now? With sine of 2 theta equals yeah, you got it. The double angle identity for sine is that sine of 2 theta is equal to 2 times cosine theta times sine theta. So on my triangle here, cosine is the ratio of the adjacent side to the hypotenuse, right? So for cosine, I'm going to write 3 divided by square root of x squared plus 9. And then for sine, sine is the ratio of the opposite side divided by the hypotenuse. And so whenever I simplify the sine of 2 theta part, that's going to simplify down to 6x divided by x squared plus 9. To get theta, I have to go back here and say that rearranging that orange equation that I boxed in green, rearranging x equals 3 tangent theta, is going to give me theta equals what? You're close. You got to divide by the 3 first, and then take the arctangent of both sides. So it'll be arctangent of x over 3. So down here, I've got 1 over 18 times arctangent of x over 3 plus 1/36 times 6x over x squared plus 9. 6 over 36 simplifies to 1 over 6. That is the answer to the second part of my integral, right? Because the first part was a little bit easier and faster. You guys suggested using trig sub for the first part, where we had 5x over x squared plus 9. But that would have been more difficult, right? We actually found the answer to the first part with just a u substitution. And so the total answer here is what I would get if I took the first part plus the second part. And so to write down my complete answer, right, the final answer here is 5 over 2 natural log x squared plus 9 And I guess x squared plus 9 is always positive, so I don't even really need those absolute values right there. But it's not a bad habit to be in. So I write 5 halves natural log of x squared plus 9 plus 1 over 18 arctangent x over 3 plus 1/6 x over x squared plus 9 plus c. That's my antiderivative. So like I said, nothing new today, actually, right? We're not learning any new strategies. But we see this, we say that's a proper rational function. Maybe we can do partial fraction decomposition to it. We do the partial fraction decomposition. We ended up getting two terms, one of which could be solved with a u substitution. The other one required a trig substitution. And then we did those strategies just like we learned in the past. Any questions about how to do this? They're kind of long problems, but kind of easy, right? Or maybe they're not easy. But with such a long problem, it can be really easy to make tiny mistakes, right? Like you accidentally forget a minus sign, or you forget to write secant squared or something. You forget the dx part. Very important to be careful. And above all, like, practice really good handwriting. Practice organizing your work, you know? I don't have perfect handwriting by any means, but man, I've seen students with some awful handwriting. And I always notice that Calculus 2 test grades correlate perfectly with a student's handwriting. Like whenever students just like have a bunch of garbled mess on their paper and they can't like read their own writing, it's impossible to work through a problem this long. Because you can't do it in your head. So I'm always interested after solving a really long problem in whether or not I got the right answer. So I'm going to do in Desmos an integral of this big ugly rational function. This time I'm going to replace the x's with t's though. So it's going to be 5t cubed plus 45t plus 3 divided by t to the fourth plus 18t squared plus 81 dt. And that's what I'm hoping my solution looks like. 1 over 18 arctangent of x over 3 plus 1/6 1/6 x divided by x squared plus 9. And that was just the trig sub part. I also have to go back and add in the 5 halves natural log of x squared plus 9 and then plus a constant. So initially it doesn't match up, but tweaking the constant means I can make the solution match. Boop. So we did it right. It's actually kind of a nice looking curve. This reminds me of the Denver airport. They've got a hotel, and the roof line of the hotel is that shape. Okay. So here's another example. Let's see if it's the same or different, or if we can learn anything else. This time, is this rational function proper or improper? Improper. So an improper rational function has a degree in the numerator greater than or equal to the degree in the denominator, so I can actually do long division first here. Anytime I've got an improper rational function, I need to start off with long division. And so long division would look like 5x squared plus 45x plus 3 divided by x squared minus x minus 6. And I'd say, how many times does 5x squared go into x squared? No, sorry, I said that wrong. How many times does x squared go into 5x squared? I'd say 5, and so then you multiply everything times 5. And when we get to this point, we stop, because now the degree of my remainder is less than the degree of the divisor. And when I stop, I can rewrite this as the antiderivative of 5 plus 50x plus 33 divided by x squared minus x minus 6. Now I'm going to have a different strategy for taking these antiderivatives. So it makes sense to separate these using my antiderivative additivity. And in the first case, that's going to be 5x. Nice. And then the second one is going to require decomposition. Even though I now have a proper rational function, it's still not really in a good place where I want to try to do anything to it. You know, if you were really, I don't know what's the right word. If you were really a masochist, you could say to yourself, I want to solve that by completing the square in the denominator and then using trig substitution. And that might be possible, right? There's like more than one way to solve a calculus 2 problem, but that wouldn't be the easiest way. Right? Decomposing first is typically the fastest, easiest way. So let's do some partial fraction decomposition to this. And we'll do that here in green. All right, 50x plus 33 over, how do I factor x squared minus x minus 6? X minus 3 and x plus 2. And so that's going to be equal to a constant over x minus 3 plus a constant over x plus 2. And I can write 50x plus 33 is equal to a times x plus 2 plus b times x minus 3. Now I think the heavy side method is the fastest way to do this. We say if x equals what? What's a convenient value for x? 3. Then the left side of my equation becomes and the right side of my equation becomes man, that's going to be an ugly fraction. Okay. And then if x equals, what's another convenient value to choose? -2. Then the left side of my equation is going to be -100 plus 33. And the right side is going to be negative 5b. So A is 183 divided by 5, and B is 67 divided by 5. It's pretty bizarre. I don't think it makes the problem any harder, but it's kind of strange fractions. So remember, we already found part of my solution. For this antiderivative, we said let's decompose it first. And now that we've decomposed it, it should be easier to take that antiderivative. And so all in all, my solution so far, my answer to this question, is going to be 5x plus whatever I get from the antiderivative of 183 fifths over x minus 3 plus 67 fifths over x plus 2 I just plugged in the a and the b. What's the antiderivative of 1 divided by x minus 3? Yep. Very good. So that's how you finish it out. So this was our first example where you had to start off by doing long division because it was a improper rational function. So we start off with long division. And then we had to use decomposition. If you just tried to go immediately to decomposing this, it's not going to work. Right? You can't decompose an improper rational function. You got to make it proper first. So we do the long division. But other than that, it wasn't terribly difficult, I don't think.